Welcome to the second lecture video of our first class time series of lecture videos. Let's consider forming different types of radicals as we continue our discussion on the allylic system in our section of delocalized pi systems. For example, here we have ethane. We're going to make a primary radical by abstracting a hydrogen and leaving one of the two electrons in that carbon-hydrogen bond behind on the carbon atom in a p-like orbital. What is the dissociation energy for that? Apparently it's 98 kcals per mole. Great. So how about abstracting a secondary hydrogen? That is either one of these two hydrogens that's bonded to this secondary carbon. That is the carbon bonded to two other carbons. We form a secondary carbon-centered radical, and the dissociation energy, the cost for that is 94.5 kcals per mole. That's a little less than forming a primary carbon-centered radical. How about a tertiary carbon radical? What if we abstract this hydrogen from that tertiary carbon that's bonded to three other carbons? We form this tertiary radical. And the energetic cost for that is 93 kcals per mole. The trend is we get lower and lower energies, and that's because there's more of a phenomenon called hyperconjugation. That is the sharing of carbon-hydrogen electron density into this singly occupied p orbital from neighboring carbon-hydrogen bonds. The more of that phenomenon that you have going on, that is, the more carbons your radical carbon is bonded to, the more hyperconjugation you have, and it's a stabilizing effect, so it lowers in energy, forming this high energy radical intermediate. How do allylic radicals compare? Well, wow. Here's our allylic radical. We'll abstract one of these hydrogens off of this primary carbon, but by virtue of being adjacent to this pi bond, there's quite a bit of electron cloud density in that pi bond that can overlap, right, with this p orbital, and the energetic cost is only 87 kcals per mole. So this is the same stability trend for saturated hydrocarbon radicals as is observed for carbocations. Tertiary radicals are more stable than secondary radicals are more stable than primary radicals. Of course, primary allylic radicals are even more stable than normal saturated tertiary hydrocarbon radicals. So the more hyperconjugation you have, the more stability you have in that radical. And the presence of a pi bond adjacent to the radical carbon makes the allyl radical more stable, that is lower in energy and easier to form, than a tertiary carbon radical. So great. Next, what do we do? Well, next, let's consider the allyl group in an SN1 reactions. You might recall from our first semester, our Chem 233, that if we put something like 1-chloropropane and methanol, we would not really get a substitution reaction through a SN1 type mechanism. That is, forming a primary carbocation and having the solvent substitute in. This doesn't really work well by SN2 either, because methanol is not a strong charged nucleophile, and if it were as methoxide, it would be a strong base, and we might get competing E2 reactions. So primary alkyl halides do not undergo SN1 reactions under solvolysis conditions that we might normally associate with SN1 reactions. However, allyl halides do undergo SN1 reactions quite readily. So in methanol, our allyl chloride will dissociate. So a chloride anion will pop off of the carbon, will form an allylic carbocation system, and now our methanol could add to either terminal carbon of this system, right? Because we have two different resonance forms for this allylic carbocation. And like I said, the real truth of the matter is something a little more complex, but it's definitely something we'll talk about in this class time series of videos. It probably will just wait until the last video in this particular series. So our methanol adds in to the empty p orbital of our allylic cation, either one on either terminal end. And once it adds in, then another molecule of methanol comes along, plucks off a proton, because methanol is a stronger base than the chloride anion. If the chloride anion had plucked off the proton instead, you would generate HCl, and of course HCl in a polar protic solvent like methanol would simply dissociate into protonated methanol and chloride anion. So we saved that step by just admitting that methanol is more basic than our chloride anion and using a lone pair on the methanol to pluck off that proton. At any rate, these are the steps of SN1. So allylic halides and allylic sulfonates undergo SN1 quite readily to give us SN1 products. So, not too much more to this particular video, but one more page I think I can punch out. The allyl cation is much more stable than the primary saturated carbocation because the positive charge is delocalized by resonance. And I know all of you know that that's not really a thing, resonance. It's just, you know, a heuristic that we use to try to understand the world until, you know, we could get a deeper understanding of what's going on with things called molecular orbitals. And we'll discuss that soon. Finally, consider the allyl anion. Here we go. Here's our propene, and now we're going to pluck off a proton and leave the 2 electrons behind on the carbon to give us our allyl anion. What's the pKa? What's the most acidic hydrogen on this propene? Well, it's our terminal methyl group, one of those hydrogens, and a pKa for that first hydrogen that you pluck off is going to be 40. That means the KEQ for this reaction is 10 to the minus 40, which means, you know, propene is not very, you know, acidic, right? It's not a great acid. It's fairly neutral, right? And another thing this means is that our allyl anion is fairly basic if you're able to form it. But everything's relative. I think we teach you that in college. If we look at propane, what's the pKa of propane? Well, about 50. So what this is saying, if we compare these two pKa's, is that our propene is about 10 orders of magnitude more acidic than propane. So propene, 10 orders of magnitude more acidic because the pKa is 40 instead of 50, right? The KEQ for this bottom reaction is 10 to the minus 50, right? And that's, you know, not a great reaction. Of course, propane is not a good acid either, right? But this carbanion formed by plucking a proton off of propane is much more basic than, you know, our allylic anion. So, what do I have to say? Geez, the allyl anion is much more stable than the primary propane anion, right? Because of resonance, which, you know, is a lie. But I'll clear that up in the next video. Hope to see you soon.